Hi everyone, my name is Matías Vera, a postdoc from CONICET Argentina and professor of University of Buenos Aires. I'm presenting a collaboration work with Dr. Rey Vega from University of Buenos Aires and CONICET too, and Dr. Piantanida from Supélec, France. With nothing more to add, welcome to Information and Regularization in Restrict Boltzmann machines. In this work, we studied the relationship between three statistical learning definitions: generalization, regularization, and information, and briefly resume these concepts. The algorithm generalization capacity is the ability to apply rules extracted from previously seen data to characterize unseen data. It's usually measured as the difference between the testing and training performance for some error metrics. Regularization techniques are learning tools used to improve generalization capacity. Examples of these techniques used on RBM are gradient weight decay, dropout, and early stopping. Finally, Shannon mutual information is a measure of the information shared between the algorithm input and its hidden representation, which some authors link it with the generalization. A paradigmatic example is the variation autoencoders, where the learning pressure is regularized by the callback label divergence, an upper bound of this metric. It's evident that these three concepts are linked, but the spirit of the work is the hypothesis that regularization techniques usually improve generalization because they decrease mutual information, at least in RBM. On the one hand, we call RBM layer a box that draws a multivariate Bernoulli random variable, conditionally independent, through an input variable. Those who have used this algorithm know that during the training stage, RBM also assumes a generative model, but our analysis can be extended to any input distribution. Note that with this model, mutual information is hard to compute for high dimension because there is a forbidden sum in the use entropy. On the other hand, we also define a RBM dropout layer by include a random variable set in the RBM layer model capable to turn off neurons on the network with probability P. Our first result is this theorem which bounds mutual information in an RBM layer. The first bound defines a computable estimation and the others relates mutual information with matrix norm, input variance, and input dimensions. Our second result also bounds mutual information but in a RBM dropout layer. The first bound presents a computable estimator for the dropout case, and the second one links this model with the first estimator. While RBM is a bit old-fashioned, the study of mutual information in this algorithm is quite recent, as can be seen in this manuscript list. I think this is related to the fact that theoretical results tend to take longer than practical ones. In fact, several times the theory managed to recycle probability concepts. Perhaps this may be the case. Okay, I start with the first theorem. Our mutual information estimator is, in fact, the sum of mutual information between the input and each hidden unit. So the first bound only uses the conditional independence. The second one is more sophisticated, but it is based on that the derivative of binary entropy evaluated in the sigmoid function is minus the identity. The third inequality is only to apply population inequality on variance. That's it. In the dropout model, E sub p is the sum of mutual information between the input and each hidden unit. In this case, the previous estimator is the sum of mutual information between input and each hidden unit, given that the neuron is turned on. In this context, the first bound uses that the conditional independence between the hidden units given the input still true. The second bound is based on the independence between the input and the noise random variable. Only this. Well, we experiment with this dataset, training with contrastive divergence, one step, standard parameters, and we increase the momentum after the first 5 epochs. It's worth mentioning the generative model used during the training stage. A joint distribution is assumed to define not only an encoder layer but also a decoder. So this can define an autoencoder which allows us to talk about mean square error or MSA. The first simulation studies the impact of gradient weight decay on the mutual information. This regularization technique includes the Frobenius norm of W as a penalization term in the loss function controlled by a metaparameter called weight cost. We measure the generalization in terms of the mean square error, expected MCA minus training MCA. And we observe that when the weight cost is modified, the behavior of the generalization error is closer to mutual information than the spectral Frobenius norm. So this fact is related to our theoretical bound and can be interpreted as the decrease of the matrix norm reduced the generalization error because it reduced mutual information, and mutual information impacts over the generalization capacity. Another way to consolidate the practical impact of our bound is by studying mutual information during the training process. Note that mutual information starts increasing until the momentum change at 5 epochs, then decrease till the epoch 76, and a slight increase begins thereafter. So, we see that the most important decrease in MCA happens when mutual information decreases, and we note a linear behavior between the spectral norm and mutual information as does of theoretical bound. So, the impact of the early stopping can also be observed on the different metrics. Expected MCA reached its minimum at 539 epochs, and from there begin a slight increase. A premature stopping of the learning process not only helps generalization, but also limits mutual information. The simulation shows the behavior of the different estimator in a dropout layer. We corroborate our bound experimentally, and we compare these dropout estimators with the mutual information estimator without dropout, because the noise is turned off after training in a dropout model. So, it can be thought that dropout regularized by reducing mutual information during the learning process. I finish with the conclusion. We showed that the different regularization methods in RBM algorithm directly affect mutual information. The studied regularization methods are gradient weight decay, dropout, and release stopping. As a continuation, we will extend the experiment to other datasets. We also want to study the models as the Boltzmann network or the Boltzmann machine, and we want to add an experimental task like anomaly detection to study the mutual information behavior when the manifold is and is not learned. And that's all. If you have questions, I'll gladly answer by mail. Thank you. We wait for you in the poster session.